Tell down, please. Oh, I need to turn on. Okay, let's start. Warm up. All right. Settle down, please. Okay, we'll continue. So just to this time with linear momentum problems. This time in 2D. Yesterday was mainly 1D, left, right only. Now we can go left, right, up and down. All right. Moving control volume, and the most complicated one, non-uniform velocity profile. All right. So we'll look at those type of problems. All right. To refresh your memory, I think the linear momentum equation, d on dt, rho u dv integral, which is this is a change of linear momentum. All right, and within the control volume plus integral rho v dot n. This one put the v also. This is the velocity vector. V dA equals to sum of forces. All right. So this is momentum, linear momentum entering. All right. Leaving minus entering. Leaving minus entering. This one the change. Change in CV. All right. Is sum of forces, and the forces we have external. External. We have normally have gravity. We can have pressure, and we can have viscous. All right, viscous. All right, these are the normal four forces that we have. Normally in this one, viscous is normally 0. Gravity also a lot of times, I put in brackets, a lot of times is 0, unless they tell you that you need to worry about gravity. Okay, so all right, so that's our equation, okay, which we normally simplify to steady state. So this one is 0, all right, normally steady state. All right, and so this one simplifies to m dot v out minus m dot v, all right, in equals to sum of forces. All right. So that's the complete equation, the first one. All right, in integral form, so that it covers everything. This is uniform velocity steady state. Velocity. All right, uniform velocity steady state, it simplifies to this. Is that okay? All right. Any questions? All right. So our example today, I just like I don't know, they call this a skid or deflector or whatever. All right. Okay. So the water comes in. Okay. This one 2D. Water comes in and deflect and goes up that way. All right. Okay. So example, let's say your m dot is equal to 2 kilograms per second. All right. It comes in at 10 meters per second. So this is our control volume. All right. Okay, again, this is an external flow problem. pressure is atmospheric everywhere. All right. What this skid or this deflector or whatever you want to call it has to do is push the water. All right. Push the water this way. Okay. So if this way. So normally they draw a nice little axis here to tell you which the positive direction. Maybe this is the X, this is the Z. Okay, so the skid will have to push the water in the negative X direction to bring it to a stop. Okay, does that make sense? Okay, and we'll have to push the water in the positive Z direction. All right, so I can already expect F external or F skid on CV in the X direction. This one will be negative, some negative value to stop the water. All right. If I don't get it, then something's wrong. F skid on CV in the Y direction to be some positive value to push the water up. Okay, so let's see that one. Okay, so again we use this one. So let's do in the X direction first. Okay, because these are vectors. Vectors you can break up into the components. All right, m dot is 2 kilograms. M dot out, V out minus m dot in, V in equals to F pressure, F viscous, F gravity, F skid on CV in the X direction. Is that alright? Can you read my writing? Cannot read, then you listen to me. I just said all of them. Okay. So in this case, pressure, this one 0, viscous 0, gravity 0. X direction no gravity. Alright. Even the Z direction. Again, this control volume, I take very small, little bit of volume only. So I can neglect it now. Alright. But if not, you need to work out how much volume is inside here. Alright. If they tell you, let's say, then what's the volume inside here, inside this control volume, then you can work it out. If not, it'll be a bit difficult. Alright. So, m dot is 2 kilograms per second. V dot out is what? In the X direction, what's the X component of this velocity? 0. Everybody agree? Alright. Minus m dot in 2 kilograms per second. V dot in 10 equals to all this 0 D F skid on CV in the X. Okay. So the answer is minus 20 newtons. Okay. F skid on CV in the X. Okay, now all agree? So the skid will have to push the water 20 newtons backwards. All right. The water will push the skid forward. All right. That's equal and opposite force. So F water on skid. Imagine if you were standing there instead of that skid, you would be pushed backwards 20 newtons. Correct or not? Backwards, I mean in the positive X direction. Okay? So water pushes in the positive X direction, skid pushes in the negative X direction. It's one pair. Alright? So if you go out on the street in Dataran Merdeka and there's this big red truck that comes around and fires at you. Alright? So you would be like that skid. You will be pushing the water in the negative X direction. The water will be pushing you in the positive X direction. That clear? Okay? So if you cannot withstand that force, then you will fall down in the positive X direction. Alright? Because this is atmospheric, there's a question in front here why F pressure is 0. Because this is atmospheric. Alright, atmosphere everywhere. So while there may be some pressure between here, alright, okay, which is not 0, that's accounted for in this term, not in this term. This term everywhere else 0. Okay. if you have a pressure gauge or pressure meter somewhere in between the skid and the water, all right, you might measure a non-zero pressure there, but that part of the pressure or force is actually taken into account in this term here, not in this term here. Right? You cannot double count. Right? Okay, so this is the x. The y direction is pretty easy. M dot out, d out, minus m dot in, d in the y direction, y direction, or no, z direction. All right, equals to, all right, same pressure, viscous, gravity is nearly zero. All right, I'll write again, pressure, that one is definitely zero. F viscous, that one is zero. F gravity, that one is approximately zero. Okay, very little water inside. But if they tell you what the water inside, then you can put up. If there's 100 grams of water, then you put F gravity is 0.1 times G or something like that. Okay, but in this case, assume the question didn't tell you there's very little water in there. Very little water in CV. Okay. All right. Okay. F and F skid on CV in the Z direction. Oh, sorry. Here should be Z as well. Okay. And M dot out is 2. What's the V out in the Z direction? Okay, if they don't tell you, alright, which a lot of times they don't, so you can assume the same velocity coming out. Alright, okay, if you go in 10, you'll come out 10. Alright, you assume it's perfect system, you never slow down or speed up. Okay, so it just comes out at 10. Is that okay? And positive because this is going upwards. Positive. Is that alright? Okay. Minus m dot in, that's 2. What's the z component of the velocity coming in? 0. Is that clear? Yeah. 0 goes to this one. And therefore, F skid on control volume in the z direction is equal to 20. Alright. So, this water, this deflector, alright, which could be you, with the big red truck shooting at you, alright, would need to push the water 20 newtons in this backwards, alright, to stop it, and we need to push the water 20 newtons up to deflect it upwards. Alright? So, if I were to draw, okay, if this was the skid, alright, this would be 20 newtons. So the total force is that one. Right? This is F skid on control volume, which is equal to, if the magnitude is equal to 20 square plus 20 square root. Alright? Add them vectorially. So, and this one will be equal and opposite pair, F water on skid. Okay? Okay, these two are equal. Is that okay? Okay. Any questions? Any questions? I think August 31st. August 30th, 31st, what? They want to go to Merdeka, Tata Merdeka again. So you might see the big red truck again. You can go there and study some fluid mechanics. Yeah. Only problem is there's not water. There's water with some thing, some thing that irritates your skin and eyes. Okay, all right. Okay, next example. All right, so in this unit, you only need to worry about fixed control volume and moving control volume. Don't need to worry about deforming control volume and all that. Okay, so the next increase in complexity example, we still have that skid. All right. Okay, so the skid, imagine like you are. So the water coming and you're running away. Okay. So the skid on wheels, right? Or you could run towards the water. So we will do two cases, running away and running towards. Okay. So in this case, you will have a fixed control volume, because if you have a fixed control volume, the skid will not be in your control volume and move away already. All right now. So you have a control volume that follows the skid. Okay. So if the skid is moving at say 5 meters per second, all right, then your control volume will move at 5 meters per second to follow the skid. Okay? Because we want to analyze this one. Okay? It's like the camera is TV camera is watching you running away from the skid. Okay? Not camera in fixed position, you're running somewhere else, then you're just filming the background, there's nothing much there. Same problem, 10 meters per second. Water coming in at water coming in at 10 meters per second, 2 kilograms per second. M dot velocity. Okay. So in this case, you need to take you can still use the same equation, but you need to take all your velocities relative to the moving control volume. All right. So V. Okay. So V in relative, V out relative. Okay. So if the V in relative, V in, comma, relative is equal to V in absolute minus V of the control volume. Alright, so the difference in velocity. Alright, in other words, if the water moving at 10 meters per second and you running at 10 meters per second, alright, so 10 minus 10, 0. The water will never catch you. Alright, you can try that also. Alright, but in this case, the water is moving at 10 meters per second. The skid is moving at 5 meters per second. So 10 minus 5 is equal to 5 meters per second. So as far as the skid is concerned, the water is coming in at 5 meters per second. Is that clear? Is that clear? Alright. Okay. So, and if it comes in at 5 meters per second, again, on the skid, we assume it's ideal case, the water doesn't slow down. So the V out relative to the skid is equal to 5 meters per second. Alright? Okay. The V out absolute is equal to V out relative plus V of the control volume. But here, I cannot do it so simply. Remember, these are all vectors. Okay? Velocity is a vector. You cannot just... Earlier, it was in the same direction, so I can just add minus and so on. But if it's not in the same direction, cannot. So this one is actually, V out relative is actually this way, going upwards at 5 meters per second, plus this one is going at this way at 5 meters per second. Alright? So the absolute velocity that is coming out in is 5 meters per second. 5, this one also 5 meters per second. Alright, V out. Absolute. Right, or relative to ground. Does that make sense? Okay. Okay. So I repeat again. So it's coming in at 5 meters per second relative to the. If you are the observer, if you are sitting on that skid, all right, you will see the water coming in at 5 meters per second, and you see the water deflecting 90 degrees and going up at 5 meters per second. Is that all right? But for observer on the ground, all right, he would see the water not only going up at 5 meters per second, but also going forward at 5 meters per second because of the skid moving at 5 meters per second. So the absolute velocity of the water going up is actually this one, 5 meters per second up and 5 meters per second this way. Right? This formula is the same as this one. What I did, I just moved this one over this side. So from minus becomes a plus. Alright, that's why here it's a plus. Okay? Is that clear? Alright? Because the skid is moving at 5 meters per second, water going upwards relative to skid. If an observer on the ground, you'll see the water not only moving upwards, but moving this way at 5 meters per second. Okay? Water on the skid is that way. Is that clear? Okay, but okay, so this is just converting between relative and absolute, or relative velocity and velocity relative to ground, and velocity relative to skid. Okay, all right. Absolute means relative to ground now. Okay, the final. Okay, so the final thing is now we'll do the same analysis, all right, as we did before. But this time, for this moving skid, okay? All right. So, in the x direction, okay, same as just now, m dot out, v out, minus m dot in, t in, equals f skid on control volume. M dot out is 2. Velocity out in the x direction, what's that? Alright. Is it 5 or is it 0? Okay. This everything, as I told you, when you use this momentum equation, use all the velocity relative to the skid. Okay. So don't use this 5. Only use this 5 here. This one. Okay. So it's actually 0. Is that right? Okay. Some look puzzled already. Alright. So as far as the skid is, when you're doing analysis for the momentum, as far as the skid is concerned, use the velocities relative to the moving control volume. The velocities relative to the moving control volume is, it comes in at 5 and it goes up at 5. Okay or not? So the in velocity, x component is 5, y component or z component, dx equals to 5, dz equals to 0. Okay, this one. Here, vx equals to 0, vz equals to 5. Alright? Alright, so we use that one. We use the velocity relative to the skid, or relative to the moving control volume. Okay? Not the absolute velocity. Absolute velocity is 10 meters per second coming in, and it's deflected and it's going out this way. Is that alright? Absolute velocity 10, and this one we don't use. It's just for you to, in case the question asks anyone. Right? We never use that in the momentum equation. We only use the relative control, the velocity relative to the control volume. Relative. V relative to CV. This one and this one. Is that okay? So, this one minus m dot in 2, velocity in 5 equals f skid on CV. So, f skid on CV equals to 10 newtons. Alright? So, earlier the answer was 20 newtons. Now the answer is 10 newtons. Right? Oh, sorry, minus 10 newtons. Alright? Okay? Because you're running away, the water won't be so painful. Right now. So okay, y momentum m dot out v out minus m dot in v in equals to f skid on CV. So m dot out is 2, velocity out is 5, m dot in is 2, velocity in is 0, is equal to this one, f skid on CV. So the answer again will be f skid on CV is equal to 10 newtons. Right? Huh? Is that okay? Huh? Sorry, Z. Sorry, this should be Z. Okay, same the coordinate up here. Here will be X, here will be Z. Okay? Yep. Move it up. Repeat again. This one don't need to add vectorially because this one, this vector is in this direction, this vector is in this direction. Right? So, huh? What is it? This one, if you add vectorially or you add this way, it's the same because the vectors are all aligned up. If they are in the same direction, then it's adding the vectors is okay. So yeah, okay. So V in, okay, V in absolute is this way, 10 meters per second. Velocity of control volume is that way, 5 meters per second. So 10 minus 5 in this way will give you this way, 5 meters per second. Is that okay? Yes. So for the momentum equation, always use the relative velocities. Never. Alright, it's just in case the question asks you what is the absolute velocity, then you find out. Alright, but you never use the absolute velocity in the momentum equation. Always use the relative velocity. Okay? So, example, alright, this one, just a quick one. What happens if you want to be brave? Alright, this is the skid. Alright, water coming in at 10 meters per second, 2 kilograms per second. Alright, m dot v. Alright, and your skid, previously we are running away. Now we run to the water. We want to be brave. 5 meters per second. Okay? So, same. Alright. This is the... Alright. Okay? Right? So, in this case, okay, alright, V in relative is equal to, what's the formula again? V in absolute minus V control volume. Alright, same as just now, which is therefore, okay, so it go around and bend, which is equal to absolute velocity is 10 meters per second going that way, minus this one is 5 meter per second going this way. So it's actually a negative. Is that right? Huh? So the answer is 15 meters per second. So the water is coming at you at 10 meters per second. You are running at the water at 5 meters per second. As far as you see it, you see the water coming at you at 15 meters per second. Is that right? Is that okay? That's why there's a 2 minus minus minus. Okay, so we can expect, all right, if you, so this velocity relative to the is 15 meters per second, well, this way, all right, these two are relative velocity, relative to CV, all right, and it goes out here. What's the what number should that be? 15 meters per second. All right. So again, if we did the ideal, okay, and if you wanted to work out what the V out absolute or relative to ground, whichever you want to call it, is equal to V out relative plus V or the control volume. Okay, so I run out of space, so I need to squeeze up here. So V out relative is going upwards at 15 meters per second, plus this one is going this way at 5 meters per second. So the answer is equal to this one, 15 meters per second, 5 meters per second. Right? So if you are run, so this is actually your V out absolute. Is that alright? Okay, so if they ask you to calculate, but again, we don't use the absolute velocity in our analysis, we only use it. So if you are running to the water, an observer would see you hitting the water pretty hard, and actually the water coming off you will get deflected forward, right? Because it's actually getting deflected this way, right? Deflected backwards. So if you run really hard, maybe you can deflect the water back onto that red truck now. All right, it's getting deflected. Okay. All right. Okay. So the x1, we have m dot out, v out minus m dot in, v in is equal to f skid on CV. Okay, m dot out, v out in the x is, okay, this should be here. M dot out, v out, m dot out is 2, v out in the x. Any out in the x? No, 0. 0 minus 2, 15 equals to f skid on CV. 2 times 15, that's equal to minus 30 newtons. Okay, so now the force, previously it was stationary skid was 20 newtons. All right, now it's increased to 30 newtons because you are running into the water. You need to push the water harder because you are running into the water. Right? In the y direction or z direction. All right, because you are running harder. Okay, the same one here. 2. Here would be v out is positive 15. All right, minus 2. V in the z direction is 0 is equal to f skid on CV, and that will be 30 newtons. So in this case, you need to push the water backwards 30 newtons in the minus x direction. Okay, remember this is our x and this is our z. You need to push the water backwards in the minus 30 newtons and upwards 30 newtons. Okay. All right. Okay. So this is the picture. I hope you got that. Okay. Yeah. Any questions? All right. Final. Any questions? Is that okay? All right. So finally, as promised, we do the third one now. So we've done moving, we've done 2D, we've done moving control volume. Now we do the non-uniform velocity profile. So remember I had that problem where I had a pipe. What's the radius? It was coming in at 30 meters per second. It was going out in a parabolic profile. Alright, the velocity equals to 60. 1 minus r squared on r squared. Alright, r is some distance here. Big R is this distance here. Is equal to half meter or 1 meter? 1 meter. Sure. Okay. Actually, it doesn't matter. Alright. Okay. So in this case, our control volume is like this. Okay. So we have a pipe or something, doesn't matter. Alright. It comes in at 30 meters per second uniform. It goes out in that parabolic profile. That 60 comes from not from the not because I say it's 60, because this one comes from mass conservation. Alright, which we did when last Friday, last Thursday. Alright, you remember not? Alright, right here you review yourself. You cannot remember from when did we do it? Week 3 Thursday. Is that correct? Okay. So review yourself. Okay, that's where I get the 60. That's the velocity profile. Alright. Here, in this one, we need some pressure. So I give you some pressure. Alright. So here, assume the pressure is equal to 100 kPa. Here, the pressure may be 95 kPa. Okay. Alright. Right. So that's our problem. Find. What do you want to find? F external to hold F external, which to hold pipe in place, right? Or our F external on the control volume, okay, to hold the pipe in place. Okay, so we start with this one. Et rho v dV. Alright, since this is steady state, so this one go plus rho integral rho v dot n. This one's a dot dV v. Alright, dA across all the thing is equal to 0. Okay. So for equals sum of forces. Alright, in this case we have F pressure and we have F external. Alright. Oh, okay. Here everything's in the x direction only, okay, this direction x equation. Alright. Okay. F pressure, F external, F viscous, F gravity. Alright, this one is 0, this one is 0. X and gravity, assume it's downwards. Viscous force for now can declare. Okay. So this creature on the inlet side is that's the density. The density is 998. Let's assume it's water. Alright, the density multiply the V dot n is actually minus 30. Is that okay? Because the normal vector is pointing outwards like this. Alright, and here the normal vector is pointing outwards like this. Okay? Because the velocity is in the opposite direction to the normal vector, that's why it's negative. Alright? Multiply by 30, multiply by pi 1 squared. Oh yeah, the color wrong. Never mind, yeah? Multiply by 30, multiply by pi, 1 squared. That's on the inlet side. Is that okay? Velocity is negative because it is going in essentially, right? And 30 is the velocity. Alright, this velocity is positive because it's going in the positive direction. Right, so this is positive. This is negative because v dot n is negative. Area is pi 1 squared. Don't need to integrate because it's a constant. So just velocity times area. Or that whole term times area. Is that okay? Okay or not? Alright. This one, I write here. This one is because v dot n is equal to minus 30. Here, v is equal to 30. Positive 30. Okay, because positive direction that way. Alright, this is area. And this is rho. Okay, that's rho. That's alright? Okay, that's the easy part. Now the next part, on the outlet side, okay, rho, okay, so we have the integral rho v dot n. Okay, now this v dot n is positive, all right, because we are both pointing in the same direction, and therefore that is just 60 1 minus 1 r squared over r squared. Okay. All right. Yeah. So this is leaving. Okay. So there's a question in front here. Someone confused a little bit because earlier this one is where? All the way up here. M dot out, V out minus M dot in, V in. Okay? But here I chose to do the left boundary first before the right boundary. So I choose to do the out first. Alright? We can. Alright? If you want to move it around, it's okay. Alright? Because I chose to do this first because it's easy. Alright? And actually, this minus sign is why it is actually minus. So it's actually this is equivalent to minus m dot in v in. Is that right? And the minus comes about because the v dot n is negative. So when you enter in, when your velocity is entering the control volume, it'll be negative because of the fact that you're entering. You're going in the opposite direction of the normal vector. Alright? And this term here, once I'm finished with it, will be plus m dot out v out. Is that okay? Right. So rho v dot n, okay, and velocity again, so 60 1 minus r squared over r squared. Rho dv dA. Remember the area integral, I can break it up into just a line integral. 2 pi r dr. So I integrate from 0 to 1. Okay or not? Is that alright? Okay, that is equal to will be equal to F external plus F pressure, which is equal to pressure times area. Pressure is 100 kPa times pi 1 squared minus 95,000 times pi 1 squared. Is that okay? Alright. So the pressure force 100,000 times the area. This is the on the inlet side. 100,000 times inlet. Here is 95,000 times outlet, and this again is the pressure outside acting in. So this the pressure vector, if I draw in purple, would be like this, and the pressure vector here would be like this. Is that alright? Outside acting in. That's why here is 100,000 positive, and here is 95,000 negative. Is that okay? Right or not? Yes or no? Yeah? Never mind, definitely in the tutorial someone will ask me, why this one negative one? Okay. Alright. I'll be glad to answer, don't worry. Okay. So here, 30 times 30 is 900. 900. So here you get 900 times rho times pi. Alright? Is that okay? Minus. Alright? 60 times 60 is 3,600 times rho times 2 pi. So plus 3,600 times rho times that 2 pi you can put together lah. So 7,200 times rho times pi. This one 2 pi rho. Okay, all the constant I take out. Here, I integrate 1 here r. Sorry, this is to be small r, not big R. 2 pi r dr. Okay, so I integrate. I get 1 times 1. I get 1. 1. This one times this one minus 2 r squared on r squared minus plus r to the 4 on r to the 4. Everything multiplied by r. Is that okay? Alright? dr. dr. This should be small r also, sorry. From 0 to big R, which is equal to 1. So 0 to 1. Is that okay? Alright? And is that alright or not? So I choose to move this R inside. So I don't want to have it outside here. So this one becomes R. This one becomes R cubed. This one becomes R to the 5. dr. Okay. This small r is equal to F external plus 5,000 times pi. Okay or not? Is that alright? 100,000 minus 95,000, that's why I get 5,000 times pi. Okay, next step, integrate. Okay, so here minus 900 rho pi plus 7,200 rho pi. Integrate becomes r squared on 2. R cubed becomes minus r to the 4 on r squared. Here 2, what do I do with 2? Divided by 4. 2 divided by 4 plus r becomes r to the 6 on r to the 4. 1 on 6. Alright, between 0 and 1 equals to plus 5,000 pi. Okay, so the last step you just put it in. So minus 900 rho pi plus 7,200 rho pi. Here we get 1 squared. You get half. Here 1 minus r is 1. So here you get r over r squared, 2 over 4 plus 1 over 6. Isn't it? Okay. And then after that 0, you get all 0 lah. No point. Is that alright? Okay. So sorry, I forgot to tell you, from here to here, I also realized that big R is equal to 1. Right? And small r, alright, now after you put in the limits of the integral, it's actually 1 also. Right? Small r is either r equals to 1, 0. Right? The two limits. Okay, that's how I got from r squared over 2 becomes 1 over 2. R to the 4, 2r to the 4 over 4r squared becomes 2 over 4. And 1r to the 6 over 6r to the 4 becomes 1 over 6. Because all the small r is 1 and the big R is 1. Yes. Alright? The limits of integral is actually 0 to big R, which is equal to 1. Okay? So, equals to f external plus 5,000 pi. Okay? So you can, everything's all done for you. You can work out yourself, x external equals to what? Alright? Just plug in the numbers and okay? Huh? 5,000 pi. Alright? Any further questions? If not, we'll stop there. We'll, I guess, need to do Bernoulli next week or Thursday. Alright. I think class want to come in, so those ones with my signature or any other further questions, when outside, I'll meet you outside. Okay.